John Mack is unusual and important because
power off, power on, power off, power on. Flip polarity. Flip it back the other way. Turn off the field. Turn on the field. Now this is with the 3 radial electromagnets by themselves without having a permanent ring magnet behind. We're still getting a lot of spin and ejection. If we flip the polarity, we still see a difference in spin direction, but some ejection. Flip it back, and it still ejects. So we don't need a permanent ring magnet. We can just use 3 radial electromagnets. When we turn off the power, we get nothing. Turn on the power again, you can see they eject. So this is one way to use electromagnets to make the ion drive work. Just 3 big radial electromagnets to spin argon gas and then drive it outward with a secondary Lorentz force. Power off, power on. Power off, power on. Flip the polarity, flip it back again. Now here we have 5 electromagnets arranged radially, and they're giving quite strong spin and ejection. When we use 5 electromagnets, you have to get this pentagonal geometry more accurate. Power off, power on. Power off, power on. Change polarity, return polarity. Anyway, we've established a general principle that radial electromagnets can make an ion drive work. This is with 5 radial electromagnets. Spin and ejection. Another way to use electromagnets in this ion drive is to make a big DC electromagnet of 0.5 millimeter wire and about 13 ohms. And you can see that'll give a nice spin of the ions when it's turned on. We take the ends of the wire coil and place them near the ends of the electromagnet. We get spin but not ejection. If we put the two ends together here, we don't only get spin, not ejection. Here it is about halfway along the wire coil. We get a lot of ejection and not just spin. About halfway along. Flip the polarity. It ejects the other way. Go back the original way and it still ejects. So that's the other way to use an electromagnet to make this ion drive work. Here's the same device with a 0.7 millimeter wire coil. The resistance is about 5 ohms. Turn on the magnetic field. You can see you're getting a lot of spin and ejection. Flip the polarity. Flip it back again. Turn off the field. Turn it on again. The ends of the Corbino disc are located about 2/3 of the way along. So 0.7 millimeter coil works just as well as 0.5 millimeter. A 1 millimeter wire coil with about 2 ohms resistance. You can see spin and ejection coming out the inside. Magnetism off, magnetism on. Flip polarity. Flip it back again. Flip polarity. Flip it back again. Magnetism off. The ejection phenomenon seems to depend on the polarity of the wire coil in this case. This is when the Corbino disc is deeper inside the coil. Turn on magnetism. Flip polarity. And it ejects in both polarities. Flip again. Flip again. There must be some subtle phenomenon here which we don't yet understand. Then when we move the ends of the Corbino disc further forward and turn on the power, one polarity, the other polarity. So it becomes polarity dependent when the ends of the Corbino disc are way in the front rather than way in the back. I don't understand the physics here. We're just making observations. For this long wire coil with wire of 1.0 millimeter thickness and about 2 ohms resistance, I had to add 250 watts of DC power from a switch mode power supply to make argon ions inside that Corbino disc spin and eject well when they're given 40 kilovolt DC between the two electrodes. Now I'm not sure what's happening when we change the polarity of the coil. Sometimes one polarity seems to work better than the other. We know we have an axial magnetic field here which will flip from north to south as we flip the polarity. There'll also be radial fields like this around the coil which may change as we flip the polarity. I'm not entirely certain of the physics. I'm just making the observations.
John Matt is unusual and important because
This now is the neon sign transformer, 30 milliamps, and 2 wire coils added in parallel. We still see a nice spin and sync of the AC signals. This is the neon sign transformer, 10,000 volts AC, 30 milliamps, with a 0.7 millimeter axial coil. Let's turn on the power. Here's a 40 millimeter Corbino disc with a couple permanent ring magnets around the outside. You can see where the ends of the Corbino disc are close to the radial center of the ring magnet. It ejects quite nicely. When we push the ends further out, so we only get a spin field from that magnet, we don't get any ejection. Then we put it back inside the radial field, and we get both spin and ejection. Power off, power on. Power off, power on.
Aire, mira para eso, ¿no?